the applied frequency must be equal to the natural frequency of the oscillating body, that is V is equal to W. And second one is the damping factor B is equal to R by 2m must be very less. Now, this can be proved mathematically by using the equation for the amplitude. We know the equation for the amplitude of the oscillating body in the case of forced oscillation is given by A is equal to F by m whole divided by square root of omega square minus p square whole square plus 4b square t square. Now, here using this equation we'll derive the condition of P is equal to omega. P is equal to omega condition will derive it using the equation of the amplitude. Now, this can also be written as square root of omega square minus p square whole square plus 4b square p square is equal to, I will write this f by m whole divided by A. Now, we will differentiate this equation with respect to P d by dp of square root of omega square minus p square whole square plus 4b square p square, and this becomes equal to 0. So, d by dp of this whole term becomes equal to 0. Now, we have to differentiate the left hand term. So, we can write 2 into omega square minus p square into minus 2p plus 8b square p is equal to 0. We will just rearrange it. This becomes minus 4p into omega square minus p square is equal to minus 8b square p. So, p gets cancelled, negative sign, and then this is 2 times 8. So, we are left with 2b square is equal to omega square minus p square, or p square is equal to omega square minus 2b square, or p is equal to square root of omega square minus 2b square. Now, this is the final expression we got by differentiating the amplitude term for the forced oscillation. P is equal to omega square minus 2b square. Now, in order to get the resonance condition, the applied frequency P by 2 pi should be equal to the square root of omega square minus 2b square by 2 pi. When the value of B is less, then if the damping factor value becomes less or becomes in the negligible, then this becomes P is equal to square root of omega square, or P is equal to omega. So, as you can see, we have got the frequency applied periodic frequency becomes equal to the natural frequency of the oscillating body through the equation of the amplitude also. In those cases, the applied frequency should be equal to the natural frequency of the oscillating body, and at that condition we will get the higher amplitude or the maximum amplitude. So, this condition is called as the resonance condition. As A max tends to infinity, B will tend to 0, and we know that P is equal to square root of omega square minus 2B square, or P square is equal to omega square minus 2B square. Now, this value of P square will substitute in the equation of the amplitude. We know the equation for the amplitude is given by A is equal to square root of F by M square root of omega square minus P square whole square plus 4B square P square. Right. So, whenever there is value of P square, we will substitute this value. So, it becomes A is equal to F by M whole divided by square root of omega square. Now, this is P square, so minus of minus omega square minus 2B square, then this is whole square plus 4B square omega square minus 2B square. Now, we will simplify this. A is equal to F by M whole square root of, this is omega square minus omega plus 2B square whole square plus 4B square omega square minus 8B to the power of 4. So, this omega square gets cancelled, and so finally the simplifying this equation, we will get the maximum amplitude A F by 2BP, or you can write A max is equal to F by 2B omega. Okay. So, maximum amplitude we will get when the damping factor is very less. So, as you can see, if damping factor decreases, there will be the amplitude increases. If the damping factor increases, the amplitude even though it is at resonance decreases. So, A max is equal to F by 2BP, or A max is equal to F by 2B omega is the equation for the maximum amplitude. Sharpness of resonance. Now this is a plot of frequency versus amplitude of the oscillating body in the resonance condition. Now that is at resonance condition P is equal to omega. Now as you can see, if the value of B is equal to 0, it is showing that the plot is showing that the infinite value, means the amplitude is maximum. Whatever the amplitude of the oscillating body is there, it will be maximum whenever the damping factor is 0 or whenever the frictional forces acting on the body is 0. And then as you can see, as the value of B or the value of the damping factor goes on increasing, what has happened? The curve, the amplitude of the oscillating body goes on decreases. Now whenever the amplitude of the oscillating body goes on decreases, it's only because of the increase in the value of the damping. Now I can call this as sharp, and I can call this as a flat curve. Now based on this graph, we can define the sharpness of the resonance. The rate of change of amplitude with respect to small change in the frequency of applied force. Now even if there is very small changes in the frequency of the applied force, then the amplitude of the oscillating body changes. Now as you can see here, in the case of the B is equal to 1 factor, and it is called a sharp curve. Now at P is equal to omega, that is at the resonance condition, you have maximum amplitude. But even if there is a small change in the frequency, either if you decrease the frequency or else even if there is small increase in frequency, there is sudden sharp changes, sharp decrease in the amplitude. As you can see here, that may say at this point. So at this point, what is happening? The amplitude of the oscillating body has decreased sharply, either if there is increase or else if there is decrease. So in both the cases, the amplitude of the oscillating body has decreased sharply. But when the damping factor goes on increases, or when the damping value goes on increases, what happens is that the curve doesn't remain sharp, the curve goes on becoming a flat. But as you can see, when the damping value has increased, even though there is either decrease or increase in the frequency of the applied force, there is no sharp decrease in the curve, or there is no sharp decrease in the amplitude of the oscillating body. Now this is completely, it depends on the value of the damping. So it can be defined as the rate of change of amplitude with respect to small change in the frequency of the applied force. So we can write sharpness of resonance is equal to change in amplitude divided by small change in frequency. So this is how we can define the sharpness of the resonance. The sharpness of the resonance completely depends on the damping. Now when the damping is 0, there are no frictional forces acting on the body, that is in the ideal condition, the amplitude of the oscillating body will be maximum. But as the damping value goes on increases, the amplitude of the oscillating body goes on decreases. Some examples of the resonance are: First one is tuning of frequency in a radio. Second one is in musical instruments. Now, in the case of first one, as we switch on the radio and then start tuning the frequency is nothing but the applied frequency to hear a very good note of the music. So, that is how the resonance can be even observed in the musical instruments also. Helmholtz resonator is a device which works on the principle of the resonance. So, what does this resonator do and what is its function? Now, in the case of resonator, particularly it is a Helmholtz resonator, it is a hollow vessel which consists of one broad opening which is called as mouth, where the length of the broad opening is represented by L, and at the other end of the resonator there is a very small narrow opening which is represented by B called as neck. So, here in the particular Helmholtz resonator, the musical notes is being sent into the Helmholtz resonator, this hollow cylindrical Helmholtz resonator, through the mouth or the opening A, which has length L, and these musical notes they keep on vibrating inside this Helmholtz resonator or inside the hollow Helmholtz resonator. When one of the components of the musical notes carried through the air has frequency same as the natural frequency of this Helmholtz resonator, what happens is that the resonance takes place and that musical notes is heard through the neck end or the neck opening which is held near our ear. So, this Helmholtz resonator is used to find out the complex musical notes. Thus, the resonator is said to be working, or the resonator is said to resonate only for such musical notes which has frequency matches the natural frequency of the Helmholtz resonator. Now, if L is the length of the neck, A is the area of cross section, capital V is the volume of the resonator. Rho is the density of air inside K is the elasticity of air. Then the period of the vibrating air is given by T is equal to 2 pi into square root of 1 by mu, or 2 pi into square root of VL rho, or T is equal to 2 pi by square root of VL by A, because K by rho. V is the velocity of sound in air, so V is equal to root of K by rho. So this is the expression for the period of the simple harmonic vibration which takes place inside the Helmholtz resonator. The frequency is given by N is equal to V by 2 pi into square root of A by VL. Here capital V is the volume and the small lowercase v is the velocity of the sound in air.